Greetings to everyone. Today we'll be presenting our project titled Optimizing Pharmaceutical Transportation Cost and Delivery Time using the Gravity Location Model. This project is part of the Supply Chain Analytics Experiential Learning course at AVI College of Engineering. In the modern logistics industry, efficient transportation plays a crucial role in reducing the cost and improving the delivery reliability. A key factor in logistic efficiency is warehouse placement. To address this, we use the gravity location model, a mathematical approach that determines the optimal warehouse location by analyzing the geographic and demand data. In this project, we apply Python-based computational models to streamline the logistic operation, improve delivery efficiency, and reduce the transportation costs. We conducted an extensive literature review to understand the existing logistic optimization techniques. The gravity location model is widely used to determine the warehouse placement for cost-effective supply chain management. Previous research paper highlights how Python-based computational models can enhance the logistics planning by integrating real-time data and optimization algorithms. Our study builds on these insights to propose an optimized pharmaceutical distribution model. This gravity location model has been widely used in logistics and distribution network to identify the optimal warehouse locations by minimizing overall transportation costs. Prior research shows that the centroid-based warehouse placement can significantly reduce delivery time and operational costs. The route optimization techniques. Several studies focus on minimizing the vehicle routes using methods like the Dijkstra's algorithm, VRP, and nearest neighbor algorithm. Research suggests that automated route planning reduces fuel consumption and enhances the delivery reliability. Python-based computational models. Recent studies demonstrate how Python libraries such as SciPy, NumPy, and GeoPy can be used to calculate the optimal routes, warehouse locations, and cost estimations. The integration of Google Maps API and machine learning models has been explored in some cases, as shown in these papers. Cost optimization strategies in pharmaceutical supply chains. Studies highlight that reducing the fleet size and optimizing delivery driver schedules can lower the operational cost without impacting delivery service levels. Our research builds upon these insights by applying Python-based automation to optimize the delivery routes for pharmaceutical transportation. And finally, the gravity location model route planning is essential for cost reduction in logistics. For the objectives of our project are optimize the warehouse location using the gravity location model, reduce transportation costs by minimizing the fleet usage, improve delivery time while maintaining service efficiency, and develop a computational model using Python for accurate cost estimation and route optimization. Our focus is on achieving these objectives through a data-driven Python-based approach to logistics planning. Currently, pharmaceutical distribution in Bangalore involves four major locations: Yelahanka, Koramangala, Kengeri, and Indranagar. However, we identified several inefficiencies. High transportation costs due to inefficient routing and excessive truck usage. Variability in driver wages based on peak hours and distance travel. To solve these problems, we propose an optimized approach, reducing the number of trucks used in distribution using a centroid-based warehouse placement to minimize the distances, and to develop an automated cost optimization model using Python. We have updated the code and made it a little complex so that we can efficiently manage all the processes and go to a more accurate reading.
Myself, Anirudh KM. So I'll be explaining about the methodology about our project. So first comes the location and centroid. So the distribution network includes four districts. So Kormangla, Elham, Tingeri, and Indiranagar. So these are the four distinct areas that we have chosen for our project. So first we have to calculate the centroid of the area services so as to approximate the central point for planning the truck routes. So next come truck routing. So given that reduced number of trucks available for delivery, so challenge is to devise optimal routes. That's the main thing, right? So first is one truck is designated to serve Elanka and Koramangala, while the other trucks delivers to Kingeri and harnesses the capability of Python software for central calculation and transportation cost estimation. So we use Python libraries such as NumPy and other libraries to determine the optimum warehouse location. Additionally, integration with APIs such as Google Maps and optimization using the libraries such as SciPy and to facilitate development computational model for transportation cost optimization and route planning. So we also use other route planning methodologies. So next comes the warehouse reload. So trucks are required to return to central warehouse after completing deliveries to one area before proceeding to the next. So this ensures the trucks are replenished with goods and ready for subsequent deliveries. So let's go on to the next slide. So next slide, we talk about the cost optimization. So that's the main thing. We have to optimize the cost while meeting the delivery deadline. Next comes the evaluation and comparison. So proposed solution should be evaluated based on its effectiveness in achieving cost savings compared to the original scenario involves higher number of trucks. So yeah, the comparative analysis of five transportation cost, driver wages, and overall operational efficiency will be conducted to assess the impact of the optimization strategy. So now let's talk about the process flow. So while it uh, while it comes to this process flow, first is data collection. So we have to gather all the data for four deliveries that is Alanka, Kormangala, Kengiri, and Indranagar. Next is center of calculation. So we use gravity location model to calculate the center of these four locations. So this step is very crucial because we have to find the center of the optimum location. This is done using Python libraries such as GeoPy and Pandas. Next comes the cost optimization, so and model formulation. So once we had Centroid, we build a cost model considering fuel cost, driver wages, rental cost, and delivery charges. So we use Python scripts integrated with Excel to automate this calculation to ensure real-time updates and its scalability. Next, we talk about route optimization and truck allocation. So existing is four trucks delivered to each location. So it optimized it by using two trucks to deliver it in more structured way. We can take one example of one truck handling Elanka and Kormangala and other handling Kengeri and Indranagar. So this is allowed to reduce the number of trucks while maintaining timely deliveries. Next comes the comparison and cost analysis. So after running simulation and calculation, we found that using two trucks instead of four resulted in 22% reduction in cost. So you can see the numbers over here from 7 lakhs to 6 lakhs per year. So yeah, next we talk about the formula used. So mainly the formula used was formula fuel cost of the truck is equal to distance by mileage into cost of fuel. So the total cost of the truck is wages into distance plus truck rate and plus material weight into delivery charges less the fuel. So that's from my side. Thank you.
Hi, I'm Shioli Halda. I will present a study on optimizing the delivery network for four key locations in Bangalore. Our methodology is designed to optimize pharmaceutical transportation by reducing cost and improving efficiency while maintaining the service quality. The key steps in our approach include selecting a strategic warehouse location using the gravity location model, which calculates most optimal position based on delivery demand and geographical spread, optimizing truck routes to reduce unnecessary trips, fuel cost, and driver expenses, automating cost calculation using Python to ensure accuracy and flexibility for future modification. Our study is focused on four key locations in Bangalore: Yelahanka, Kengeri, Koramangala, and Indiranagar. Instead of relying on guesswork, we use Python's GeoPy library to determine the center of these locations. The calculated optimal warehouse location is Gandhinagar Racecourse, which minimizes the total travel distance for all deliveries. This methodology ensures efficient distribution, cost reduction, and improve logistic management. Initially, our system has four separate trucks, each handling one delivery location. While this method ensures direct deliveries, it led to high operational costs due to increased fuel consumption, wages, and high maintenance. To optimize this, we paired locations strategically. Now, Truck 1 serves Yelahanka and Koramangala. Truck 2 serves Kengedi and Indiranagar. By consolidating trips, we reduce the total number of trucks from 4 to 2, leading to significant cost savings in wages and fuel. This method is similar to how ride-sharing services optimize routes, pairing passengers heading in the same direction reduces fuel cost while maintaining services efficiency. Likewise, in our model, two trucks now efficiently serve all four locations, cutting cost without compromising the service quality. Instead of carrying all deliveries at once, the trucks will return to warehouse between the deliveries for reloading. This approach offers several key advantages. A, it helps prevent overloading, ensures trucks are not carrying excessive weight, which could slow down deliveries. It reduces delays. By reloading between trips, we ensure that the batch of deliveries is fresh and aligned. For example, in pharmaceutical logistics, temperature sensitive medicines need to be delivered promptly. By returning to the warehouse between trips, we minimize delays and maintain product quality. Thus, reloading at a centralized location ensures faster turnaround time, avoids delivery bottlenecks, keeps the supply chain agile and efficient. A major goal of our study was to reduce the transportation cost while ensuring timely deliveries. We broke down our cost structure. The first is fuel cost calculation. The formula uses distance divided by mileage into the cost of fuel. The mileage which we have assumed is 22 km per liter, and the fuel price is 87.58 per liter. The driver wages optimization. Next, initially our driver wage was rupees 40 per kilometer due to fewer trips per driver, which our optimized model turned it to rupees 30 per kilometer, as now each driver covers more locations efficiently. Our process started with first collecting geographic coordinates, demand and demand data. The four key locations, these locations had varying delivery demands and distances. To identify optimal warehouse location, we applied the gravity location model using Python. This calculates the center of the point which minimizes the total travel distance across all locations. Then we use Python libraries like GeoPy and Pandas, which we automated this process. The result was our warehouse was optimally placed in Racecourse, Gandhinagar, ensuring equidistant delivery and cost-effective transportation. We calculated the After determining the warehouse location, we built a cost estimation model considering multiple factors: the fuel cost, which is calculated based on distance and mileage, driver wages, which are adjusted according to optimized routes and coverage area, truck rental and material weight based charges integrated into final calculation. Instead of manual calculation, we used Python scripts which integrated with Excel to automate the entire cost estimation process. This ensures real-time updates and allows easy modification for future scalability. This approach makes a model highly adaptable, meaning business can tweak it to suit their specific delivery needs without redoing the entire manual calculation manually. This is the calculation. To validate our model, we compare the two different scenarios. Before optimization, 4 trucks resulted in a total annual cost of 7 lakhs 91,992. After optimization, total trucks resulted in a cost of 6 lakh 14,392. The annual savings achieved was rupees 1 lakh 77,600. So there was a cost reduction of 22.4%. By consolidating deliveries into 2 trucks, we ensured lower transportation cost, efficient driver utilization, efficient minimal impact on delivery time. These savings are substantial and can be significantly improve profit margins for business operating on a large scale. Initially, we performed these manual calculations to establish a cost baseline. However, this method was time consuming, prone to human errors, and difficult to scale. But with Python automation, the eliminated calculation errors were limited, integrated real time cost updates, which allowed businesses to easily test different delivery scenarios. This approach ensures long term scalability, and this is adaptable across multiple industries, marketing, logistics, planning, smarter, and more efficient. To summarize, the optimized logistics model achieves significant cost reductions and operations involved 22.4% of the reduction in transportation cost, only an 8.1% increase in delivery time, well within the acceptable limits, reduce the fleet size from 4 trucks to 2, improving the cost efficiency, the scalable model that can be applied to multiple industries. Beyond pharmaceuticals, this model can benefit e-commerce, FMCG, and retail industries where supply chain is efficient is where supply chain efficiency is crucial. By integrating Python-based automation, smart routing, and warehouse optimization, we paved a way for data-driven, cost-effective supply chain solution.
Hello everyone, my name is Ezil Surendaryu, USN 1RV21ME026. Now I'll be talking about the update we have done on this project. Uh, in our updated work, we have significantly enhanced our optimization model by implementing advanced algorithms and refining our warehouse location selection process. These improvements have led to better cost efficiency, reduced travel distance, and more effective resource utilization. First, we have in the initial model, we used a simple centroid calculation to determine the warehouse location. However, in this updated model, we introduced a weighted gravity model that considers both geographical coordinates and the demand at each location. This ensures that the warehouse is positioned not just based on the distance, but also on the actual demand patterns, leading to more efficient deliveries. The calculation used for this are to find the x coordinate and y coordinate of the warehouse. We find the ratio of summation of xi into demand of I, that is the demand of each warehouse or location divided by total demand. This means that location with higher demand have a greater influence on the warehouse position, ensuring that the warehouse is centrally located based on actual logistic needs. By using the weighted gravity model, we minimize the total transportation distance, leading to reduced fuel cost and faster delivery times. This improvement ensures that the warehouse is optimally placed to serve high demand areas more effectively. Now, coming to the second change. Previously, route planning was done manually, which was time consuming and prone to errors. In the updated model, we automated this process using the nearest neighbor algorithm, or shortly NNA. NNA is a heuristic algorithm used to solve the traveling salesman problem, which is highly relevant to our route optimization needs. How does this algorithm works? The algorithm starts from the warehouse and selects the nearest delivery location, while ensuring that the truck's capacity is not exceeded. This process is repeated until all locations are assigned, and then the truck returns to the warehouse. This approach reduces the total travel distance and ensures that the deliveries are completed within the available time window. What are some of the benefits of NNA? The travel distance are reduced by always choosing the nearest location. The algorithm minimizes the total distance travel, leading to lower fuel cost. The algorithm ensures that the trucks are used optimally, reducing idle time and improving overall efficiency. The NNA can be easily scaled to handle more location and trucks, making it a versatile solution for larger distribution network. In the sense, the scalability of this project and that algorithm is very good. Um, Coming to the code of the which we have used for this project. As you can see, this is the Python code which we have used. This code, when it is running, it will provide an Excel sheet which I'll be showing in the upcoming slides. The main key features of this code are location data structure. It manages 8 delivery locations in Bangalore, namely Yelahanka, Kengeri, Koramangala, Indranagar, Electronic City, Whitefield, Mahatali, and JP Nagar. Each location has coordinates x comma y for position mapping, demands in kilogram, time window for deliveries, and service time in minutes for each delivery, which is given as shown. And coming to the next parameters are the vehicle and cost parameters. It includes capacity, which we have constrained it to 600 kg per truck. Maximum route time is 8 hours. Speed is 40 km per hour. Fixed cost is 2000 rupees per truck. Variable cost is 40 rupees per truck. Fuel efficiency, we have kept it at 22, which can be changed depending on the vehicle and the traffic and stuff. Fuel cost is 87 rupees. Coming to the algorithms which are used, we have used a gravity location model. Then you can see these are the two uh, formulas which are used for weighted gravity location model, which minimizes the overall transportation cost by locating a central warehouse based on demand. Coming to the route optimization, we have implemented a clustering based approach using a nearest neighbor algorithm. And the steps of the algorithm are starts from the warehouse, finds the nearest unassigned location, checks capacity constraint, builds routes incrementally, and returns to warehouse. And after the routes are finalized, we calculate the cost, fuel cost based on distance and efficiency, variable operating cost per kilometer, fixed cost per truck, and total route cost. And at the end, we generate an Excel report containing all these features. Once this code is executed, these are the code for to generate the Excel sheet. We get the Excel sheet in such a manner which shows about which has four pages or sheets. In the executive summary, the total routes, distance, overall cost, average cost per route, central warehouse location, vehicle capacity, all the information of such are located in this. Go to the route detail sheet. This shows the individual route information of each truck. For example, route 1 warehouse to Mahatali to Alanka and back to warehouse. Distance, load taken by the truck, and as you can see, it does not cross 600. And based on the route, it calculates fuel cost, operating cost, and gives us the total cost. Coming to cost analysis, it sums up all the fuel cost, variable cost, and fixed cost, and gives a total cost of about 21,242 per month. And the location data for all the areas which were selected is given, x coordinate, y coordinated, and time window start and end, and its service time. Uh, Coming back to the results of uh, when we have done like before optimization, if we consider like each truck going to 8 selected areas, the total cost comes up to 28,208 rupees. This is the cost analysis table when one truck goes to one location only. It goes from the warehouse to the location, comes back to the warehouse, which is comparatively more, it's not efficient and it's waste of resources. In the initial scenario, we used one truck per location, resulting in 8 routes with a total distance of 277.58 kilometers and total cost of rupees 28,208. The average cost per route was 3,526 and the warehouse location was 38.13, 31.52. After applying the weighted gravity location model and the nearest neighbor algorithm, we reduce the number of trucks from, or we can tell that we reduce the number of routes from 8 to 5. The total distance traveled decreases to 255 kilometers and the total cost dropped to 21,242 rupees. The average cost per route increased slightly to 4,248 rupees, but this was offset by the significant reduction in the number of routes and overall costs. The total transportation costs were reduced by 24.7%, saving 6,966 rupees compared to the pre-optimized scenario. The total distance traveled decreases by 21.96 kilometers, reflecting more efficient route planning and reduced fuel consumption. The number of routes was reduced from 8 to 5, indicating better utilization of trucks and drivers. Coming to the conclusion of our project, by implementing the weighted gravity location model and nearest neighbor algorithm, we achieved significant improvements in the transportation network, and the transportation cost was reduced by 24.7%, and the distance was also reduced by 21.96 kilometers, and the number of trucks used were reduced from 8 to 5. Coming to scalability and automation of this project, the use of the computational models and Python-based automation allows for accurate cost estimation and route optimization, making the model adaptable to various industries and scalable for different datasets. The automated system ensures that the model can handle dynamic changes in demand and route conditions, providing a flexible and robust solution for future needs. And this is a future-ready model. The updated model is not only more efficient, but also ready for further enhancements such as integrated real-time traffic data, optimized vehicle load capacity, and exploring multimodal transportation options. This makes a solution a sustainable and scalable option for the evolving needs of a logistics and supply chain industry. Thank you.
Now let's look into the future scope. So first is the dynamic traffic condition. So integrate real-time traffic data from Google Maps API to adjust routes dynamically. So each time the traffic gets updated, the route also get updated accordingly. So that's the future scope of our project. So next is vehicle load optimization. So use optimization technique to maximum capacity utilization by reducing the number of trips. So that's the main objective of route optimization, which further leads to cost reduction. So next is multimodal transportation. So explore hybrid transportation options such as rail, air, drones for long distance deliveries. Carbon emission and sustainability. So implement CO2 emission tracking and develop eco-friendly routes to minimize environmental impact. Next is demand forecasting and seasonal adjustment. So use machine learning models to predict demand variation and dynamically adjust truck allocation. Next is advanced route optimization with AI. So use AI algorithms such as genetic algorithm and ant colony optimization for intellect routing. Next is dynamic pricing for daily driver wages. So implement surge pricing models based on demand and delivery schedules. So next is warehouse multi-hub optimization. So to extend our gravity location model that we use to dynamically select multiple distribution hubs. Next comes the risk and uncertainty model. So incorporating stochastic models to account for unexpected delays due to weather or road condition. Next is integration with IoT for fleet tracking. So use IoT sensors and GPS tracking to monitor trucks in real time and predict maintenance leads. Thank you.